The history of materials is a fascinating study, and we find that if we look back in the ancient literature, we can find books like Agricola's book. We can find a book called Pyrotechnia that was written by Baron Guccio in 1540, in which he described many of the casting processes and the metallurgical processes that are used today. But for years and years, people have been interested in this characterization of materials by mechanical strength. And we know from drawings that we have out of the very early centuries that people like Leonardo da Vinci was interested in strength of materials. He was interested in how much a given material would support. And so we can concoct a little exercise that will show us a problem that he had, as well as a problem that most neophytes have in the field of comprehending mechanical testing diagrams. Actually, let's just suppose that someone like Leonardo da Vinci decided he'd like to make something. He wanted to know the strength of material. He wanted to use the minimum dimension that he could in his piece, and so he wanted to know how strong a piece of material was. Let's suppose it was amber or glass or something like that, a piece of isotropic material like glass. And let's suppose that he said, I want to put a weight on this, and I want to find out how much it stretches. And I'll take the weight off and find out if it goes back. I'll find out if it's elastic, and I'll find out what its elastic limit is, and I'll find out under load how much it really stretches. And so he did this exercise, and he got a plot. And his plot was load versus extension, and it told him exactly precisely what the elastic parameter was that he was looking for, called the modulus of elasticity. And so he wrote his friend in another city, and he says, I find this superlative material, and I want you to try it. And he sends him the prescription of what he had, and his friend says, oh, I have a piece of that. And he goes out and he gets a piece, and he tests it. But lo and behold, although it's exactly the same material, when he puts a load on it, he doesn't get the same value. It doesn't stretch as much, or it stretches too much, and it doesn't have the same slope, it doesn't have the same modulus of elasticity, but it's identically the same material. Now what's wrong? Well, if we look at this first slide, we can find out a little bit of what's wrong. And that is to say, see, Da Vinci may have taken the material, which was, let's say, the B material, and said, I have a piece of the B material that's that big as the little crosshatched square shows it to be, and he moved it up along the elastic line. He traces it from the origin, moving it up to the point B, and he says, okay, that's as much as it will go elastically, and that defines the material. That's a load deformation or load elongation plot. His friend, when he got the prescription, didn't have a piece of material that big, and so he took a piece of material that was just, say, half that size or a quarter that size. And when he tested it, when he hung the weight on it, he found that, gee, it stretched a lot more. Its elastic behavior was different. Well, what was found out in very early days is that all we had to do was to normalize these curves. And we normalized the curves by putting them together so that we have the load that we had in each case divided by the cross-sectional area. And we call that the stress. And we say, we're going to put the elongation over the original length, normalize it in that way, and that will be the strain. And now we take the two curves that we had before, and they'll plot up to be the same curve for A and B. And this particular elastic curve now, if the end of the curve was the elastic limit for the material, will describe a lot of things for us. So, for instance, a man named Young, working with this back in the 18th century. I believe that's right. Worked with this. He called the slope of that curve the modulus of elasticity, or it's referred to as Young's modulus today by most everybody. And he did a lot of other things. For instance, he found out that the area under that curve is a measure of energy. For instance, the stress that we have is in pounds per square inch. That's the stress units, pounds per square inch. The strain is in inches per inch. And if we find the area under the curve by multiplying those two together, then it becomes inch pounds per cubic inch, or energy per unit volume. And that's referred to as the modulus of resilience. And so here we haven't moved very far along this pictorial curve now, and already we know that that simple little curve tells us something that's unique about the material, modulus of elasticity, and describes for us the modulus of resilience if we know its limit. Well, how do you establish the limit? You establish the limit by running a more complete curve, and this would be a characteristic curve for some material, say a material like copper, and we find out it has some unique things to tell us. Actually, the area under the entire curve is still going to be an energy term, and it's going to be, say, inch pounds per cubic inch. Energy required to elastically deform the material, plastically deform the material, and finally to rupture the material or to generate two new surfaces, at least two new surfaces in the material. It would require all of the energy that's under that particular total curve. And on the curve we could look at the elastic limit for the material. We could find out that the elastic limit may be at a point right here where it ceases to be a straight line. We generally refer to that point as the proportional limit. But anything below that's elastic. It's not the true elastic limit at all. The elastic limit may reside somewhere in the curved part of that material. And the only way we find it is by loading the material up to that point, unloading it, see if it goes back to zero. When it ceases to go back to zero, we've just passed the elastic limit. Then we get on this particular part of the curve and we find that, hey, it has taught us something that's really tremendous. And we learn this, by the way, by looking at a specimen that we just did in the last class, where we plastically deformed the material. We elastically deformed it and plastically deformed it. And the question we have to ask is, does the material get stronger or does it get weaker when we do that? That's a fundamental question. So let me see if you can show me your hands. How many of you think it gets to be stronger? Would you show me your hands? And how many of you think it gets to be weaker? Show me your hands. And let's see, we still got somebody out there that doesn't think, if I counted right. Well, we're going to run a little test. And I think the young lady said she thinks it gets weaker, right? So I want you to come up here with me, if you will. And it's going to get this gentleman to come up here with me, too, if he will. And stand alongside of me. And what I have done is I have prepared, you're going to have to stand close to me so we all get a pretty picture. I have prepared a specimen, and if you had the specimen in your hand and you looked at it, you'd say, what's the grain size? Well, nobody could describe the grain size in this particular material, because from this point, where I have my finger to that point, it's just one single crystal. Do you see it is? And from here to here, it has one grain size, and would be hard to describe because it's kind of a modeled grain size. Now, actually, we were trying to make one single crystal out of this bar. And if we had succeeded in making it one single crystal from this end to that end, I wouldn't be up here using it in a demonstration. I'd sell it for about $200. That's what they sell for. But since it isn't any good, when we're going to destroy it. So you can see that it's a single crystal part in it and a polycrystalline aggregate up here. And so what's your first name?
Dorothy.
Dorothy. Dorothy, you think you could bend that thing?
I'll try.
Okay. I want you to hold it up about like right there. Put your fingers, your thumbs right in the middle and see if you can bend it. All right?
Oh.
I won't put her in jail, will we? More? Give it a real old good heave-ho.
Oh, That is strange. It's harder.
Well, we'll see. Maybe you're just getting tired. And Lawrence, is it?
Yes.
Lawrence, how about you holding it about the same level now? Put your thumbs in it, and let's see if you just straighten that right back out for her. Or you want to see if you can bend it some more first, if you want to try that. See if you can straighten it.
Seems to have gained strength.
But you didn't do it the first time, so you really don't know. And you know you have to run, when you do a test like this, you got to be fair, right? Because she's littler than he is, but she may be stronger than he is. And so Dorothy, just do it again, really. And just like you did before, and just rip it right down, right?
What did you do to it? I must be getting very tired. I can't do it.
Well, now he can actually bend it. He's stronger. He can bend it again. So you just bend it double for him, Lawrence, and show him. Now hold it up in the air so they can see how it is bent. Now we'll give him the tough job. Now you straighten it back up.
I doubt if I can do it.
Well, okay.
Getting stronger.
All right, thank you very much. Now we learned something out of that, right? But we didn't have to do this test. The diagram told us that just now. And what it really says is, if you plastically deform a material, it gets harder. It doesn't get softer. Everybody knows that. I mean, even those girls of mine that used to put those bobby pins, they do anything with a bobby pin. You know, they pick a lock, repair a carburetor, and they know that if they need just a piece of wire that long, if they bend it back and forth at that same spot, then it'll break. But did you ever notice it never wants to bend at the same spot? Why? Because it got harder, and it's soft over here, right? So when you plastically deform a material, it gets hard. Okay, let's go back to that last slide now. And if we look at that last slide, we'll find out, hey, the information was there right along. It told us that if we come up elastically, we start plastically deforming the material. Every time we deform it, the yield strength of the material is higher. That says if we unload the material, it will unload by coming down like this, and then if we load it back up, it'll go up to that new value. It'll get harder and harder and harder, till finally it gets up to the ultimate strength. At that particular point, it seems to go down. Now we have to address that a little bit later, but there's a value that we need to know in addressing these characteristics, which is the elongation to fracture. We generally just call that elongation, and many times refer to it as the ductility. And what we do is we pull the specimen all the way in two, put it back together, find out how much residual stretch we have in it, and that's called the ductility. We express it in percentage of the original length. And so, for instance, a piece of steel may have 18% ductility or 18% elongation to fracture. It means its residual elongation to fracture would be 18%. Well, if we look at this curve now, it looks different than the last curve. The last curve would be characteristic, say, of a piece of copper. This curve is characteristic of a piece of steel. And we find that we have a funny little bump in the curve. We have a stress-strain curve. We load it up elastically. It comes up along the curve. Finally gets to a point where it goes back down again and then begins to strain harden. Harden as we've just seen the aluminum bar go. Well, number one, we have names for this. We call this particular point, it's shown out here on the side, as the yield point. It means this stress value is the yield point. It's the yield stress. It's called the upper yield point and the lower yield point. But that is the point. You notice it ceased being linear back in here somewhere, but that is the elastic limit of the material. And this kind of curve is developed in what's called a hard machine. It's a machine that's being pulled at a constant rate. So it just says the material plastically deforms and unloads the machine, and then the machine has to catch up with it and loads it back up to the ultimate strength.